which is analytic functions as mappings and Mobius transformations. As for an introduction, we are starting with finding the nature of the function f of z is equal to z square. Suppose we are thinking about the same function, and suppose if z is equal to x plus iy, then you know that f of z is equal to z square, which is equal to x square minus y square plus 2xy into I. And if we are thinking about the real part of f of z as u and the imaginary part of f of z as v, we know that the real part will be x square minus y square and the imaginary part will be 2xy. Right. Now let's think about a set of points. Okay. In this set, you are having complex numbers such that the real part is x and imaginary part is y, and x square minus y square is equal to some constant c. Okay. So this c is necessarily a real number. And we know that x square minus y square is equal to c is an equation of a hyperbola. Okay. Now we are going to apply our function f of z is equal to z square on the points of this set. Okay. So you have f of z is equal to, earlier you said it is x square minus y square plus 2xyi, and in this set we are considering every point has x square minus y square to be equal to c. So instead of x square minus y square you can replace it with c. So f of z is equal to c plus 2xyi. Now think about the real part of this function f of z. So that we call as u, and here it is nothing but c. Right? So in this set you are getting, if you are applying the function f of z is equal to z square, we know that the real part of the image of the point will be c. And suppose we are thinking about the points in the set of complex numbers x plus iy, where 2xy is equal to some real number d. Here also you note that this 2xy is equal to d or xy is equal to d by 2 is the equation of a rectangular hyperbola. Okay. So you are applying our function f of z is equal to z square on this set of points. So you get f of z is equal to x square minus y square plus, instead of 2xy, the point satisfy 2xy is equal to d. So instead of 2xy you can substitute it with d, right? So when we are thinking about the imaginary part of the function, the point, the imaginary part, you're getting the imaginary part to be equal to d. So we call it v, right? So v is equal to d. So this is what we got now. Okay. Let us picturize what we got now in two planes. Okay. So for that, you had the domain set to be the first set here, the set of points here, and the second set here, right? So I am going to plot these two of the sets in one plane, xy plane. Okay. And before that, I am assuming that the C and D sitting here are not equal to 0. Okay. And for instance, say for our clarity of our inference, I am going to take C to be equal to 1 and D to be equal to 2. Okay. So let's see the figure. So in this figure, you can see you had first of all the set of points x plus iy, where x square minus y square is equal to c, right? So instead of c you have 1. So you are thinking about x square minus y square is equal to 1. That is a hyperbola. We said it is a hyperbola, and when we plot you are going to get the set of points which are colored pink. Okay, this is the hyperbola x square minus y square is equal to 1. So that is the pink points. Okay, pink set of points. And the next one was that 2xy. Next set of points was that all those x plus iys satisfying 2xy is equal to d. Instead of d we took 2, right? So you will be getting 2xy is equal to 2, that means xy is equal to 1, and that is a rectangular hyperbola, and that is marked blue here. Okay, xy is equal to 1. So you are having the xy is equal to 1 here and the xy is equal to 1 here. Okay, so this is the domain we are talking about. Okay, now you applied f of z is equal to z square on the first set, x square minus y square is equal to 1, the points on sitting on this hyperbola. Okay, and then what you got is, just let's let's check it. You what you got, the image is u is equal to c. So instead of c you are having 1, right? So here the, that's a small, so here this u is equal to, u is equal to 1 will be the set of all points which are mapped from the hyperbola x square minus y square is equal to 1. Okay, and similarly we said in the second part that we are considering the hyperbola xy is equal to 1, set of all points of the hyperbola xy is equal to 1, right? So when this xy is equal to 1 is mapped by our function f of z is equal to z square, we said we will get b is equal to d, right? So the d we are taking here is 2. So now instead of 1 here, that will be 2. Okay, just think that this is 2. This one will be 2. Okay, so v is equal to d, that is v is equal to 2 is the image of the set of all points lying on the hyperbola 2xy is equal to 2. Okay, so that is the set of all images of the points coming from that hyperbola. Okay, so we are familiar with mapping a domain in the complex plane to the range in the complex plane. Earlier, we are while we were discussing about complex mappings. Okay, that is what we did here. So here we want some kind of observation. Okay, so in the first xy plane, we are having two sets. The first set is a set of all points in x square minus y square is equal to 1. And in the second set, we are having the set of all points in the hyperbola xy is equal to 1. Okay. So we are thinking about the intersecting points and the intersecting angles. Okay. So this is one among the point of intersection, right? And this is also one among the point of intersection. So you can just forget that. So you are having 2 points of intersection. Okay. So in this, when we are thinking about these points, think about the intersecting angles also. Okay. So in order to find the intersecting angles, what should you do? You should draw the tangents at those points for each of the curves. Okay. So when we are drawing the tangent for this, you'll be getting the tangent here, and the tangent for the xy is equal to 1 here, you will get the tangent to be here, and when they are intersecting, we are getting that to be 90 degree, intersecting angle to be 90 degree. Here also, if you are thinking about x square minus y square is equal to 1 and xy is equal to 1, it is intersecting at this point and we are drawing the tangents of that point on these curves. Here also you are going to get 90 degree. Okay. This is one fine observation you get from here. Now you're going to think about the image of both of these hyperbolas. Okay, the first hyperbola we said that the image will be u is equal to 1. The second hyperbola, the image will be v is equal to 2. Okay, so these image also intersects at 90 degree. So this is some kind of we feel that it is some kind of coincidence maybe, but as we move on we will come to know that this is not at all a coincidence. Okay, so the two hyperbolas we discussed here are intersecting at right angles, and also the corresponding images under our function f of z is equal to z square is also intersecting at right angles. This is what we just found out now. Now consider two cases. Okay. The first case is that the real part of a complex number is c, a real number, and y is arbitrary. Okay. So when we are applying our function f of z on this c plus iy, right? So you're going to get it as c square minus y square plus 2cyi, right? If you are thinking about f of z to be equal to u plus iv, you are getting u is equal to c square minus y square and v is equal to 2cy. And from both of this, what we are going to do is we are going to eliminate y. For that, first in this equation, find y square. That is y square is equal to c square minus u, right? That is nothing but minus of u minus c square. Okay, now in this equation, square both sides. That means you will get v square is equal to 4 into c square into y square. And instead of this y square, substitute what we got from the first equation. That is minus 4c square into minus of u minus c square. To obtain v square is equal to minus 4c square into u minus c square. So what we obtained is how the image looks like, right? So here we have x is equal to c and y is equal to y is arbitrary. Then you're going to get a set of points u plus iv such that the u plus iv is satisfying this equation star. Okay, this is what you get from case 1. Okay, now instead of this x is equal to c, suppose if we are having a negative real number, that is x is equal to minus c, then also when you work out, since we are squaring the equations, you will end up with the same equation star whenever x is equal to minus c and y is arbitrary. Now suppose we are thinking about the case x is arbitrary and y is equal to a real number d. Okay, apply a function on the set of points x plus iy, such points. So f of z is equal to, you are going to get x square minus d square plus 2dxi. Okay, if f is equal to u plus iv, you are going to get u is equal to x square minus d square and v is equal to 2dx. Okay, here we are going to eliminate x. Okay, so in this equation, the first equation, we are having x square is equal to u plus d square, and since v is equal to 2dx, we will have v square is equal to 4d square x square, and instead of x square you are going to substitute u plus d square. So finally you are going to get the equation double star, which is v square is equal to 4d square into u plus d square. Okay. So you consider two cases, and in this case also, if the y we are taking is a negative real number, then also when you work out, you try to work out, you get the same equation double star here. So you got two equations, right? Here see, we are having v square is equal to minus 4c square into u minus c square. So here you have a square of v, the variable, and in the right hand side you are having the variable u, which is having degree 1. So when you take a closer look at the equation, you understand that it is something like the equations we saw for parabolas, y square is equal to 4ax kind of form, right? So this is nothing but a parabola, and when you look at equation double star also, you know that this is also a form of a parabola, general form of a parabola. So the equation star and equation double star are parabolas. Now we are going to find if they intersect the two parabolas. Okay. So you have the two equations here and you're going to equate them, and equating you get at a point of time where you get u into c square plus d square is equal to c square plus d square into c square minus d square. Okay, these are all very simple evaluations. So here you can strike out c square plus d square, since c square plus d square is never 0, as c and d we already took them to be not equal to 0. So we can strike the c square plus d square on both sides, and what you are ending up is u is equal to c square minus d square. And substitute the u in any of these equations of the parabolas. I'm going to substitute in the first equation. So v square is equal to minus 4c square into, instead of u, substitute c square minus d square minus c square. Cancel out the c square and you're going to get minus 4c square into minus d square, which is equal to 4c square d square, which is nothing but 4 into modulus of cd the whole square. So we are using the modulus because we are going to take the square root of that for taking the safe side. So here v is equal to plus or minus 2 into, when you are taking the square roots, you get modulus of CD, right? So the point of intersection of the two parabolas we had end up with is UV, O dot pair UV, which is equal to the O dot pair C square minus D square, U is equal to C square minus D square, comma plus or minus 2 into modulus of CD. That means you have 2 points of intersections for this, two parabolas. Okay, here when z is equal to x plus iy such that x is equal to c and y is arbitrary, that means in the first case, when we applied the function f of z is equal to z square, we got the parabola sitting here. And suppose if we are tending this real number c to 0, okay, when we are tending it to 0, you know that u minus c square will be tending to 0, right? And the c square will never be a negative number, right? And here you are having a minus sign, so this v square will always tend to the negative real axis. That is an observation we get from here. And something similar to this is being added as we go on. Suppose if G is the slitted complex plane, okay, excluding the negative real axis and 0, we are going to apply f of z is equal to z raised to 1 by 2 on this region G, open connected set G. Okay, and we proved earlier that when we are dealing with the principal branch of z raised to b, the powers of z, we said that z raised to b is equal to e to the power b into logarithm of z, where this log of z is nothing but the principal branch of the logarithmic function. This is something which we proved a lot of time when we are dealing with the logarithmic function. So here z raised to 1 by 2. So instead of this b, we are having 1 by 2. So this is equal to e to the power 1 by 2 into logarithm of z, where logarithm of z is the natural log. It is not the natural logarithm, it is a branch of the principal branch of the logarithmic function. And when we are thinking about the principal branch of logarithmic function, we said that we were considering the slitted complex plane, which we already took here. Okay, so we don't have any clashes there, and we already know that that principal branch is defined as the natural logarithm of modulus of z plus I into the argument of z, right? So this we know that this argument will be lying in between, strictly lying in between minus pi and pi in this slated complex plane. And then just open the braces, you get e to the power 1 by 2 into natural logarithm of z plus I into theta by 2. And then apply the property of the exponential function, that is nothing but e to the power the natural logarithm of here, since it is natural logarithm, we can write it to be ln of modulus of z the whole raised to 1 by 2. That is a property of natural logarithm. And by the property of exponential function, you can write e to the power a plus b to be equal to e to the power a into e to the power b. That is what we done here. And then up here we did the property of the natural logarithm. And since this is the natural logarithm, we know that this is equal to modulus of z the whole raised to 1 by 2. And e to the power I into theta by 2 can be rewritten as cos theta by 2 plus I sin theta by 2, which is a property which we had done while we were thinking about the exponential functions and its properties. Now here, since we were dealing with the principal branch, definitely theta is lying in strictly lying in between minus pi and pi. That means theta by 2 is strictly lying in between minus pi by 2 and pi by 2. So cos theta by 2 or cos of minus theta by 2, whatever it is, the values will strictly lie in between 0 and 1. Okay. So if you are opening the braces, you are getting the real part to be this and the imaginary part to be this. Okay. And when we are considering the real part, we are understanding that this cos theta by 2 is coming strictly in between 0 and 1 and it doesn't take the value 0, right? Because it is strict inequality. And also this modulus of z will never be 0 because we are not at all taking z is equal to 0 because we are considering the slitted complex plane. So definitely this real part which we now end up with will be strictly greater than 0. Okay. So think of it to be u plus iv. This f of z is equal to, you obtain something and that is equal to u plus iv. So u is this and u is strictly greater than 0. So now we are thinking about the range of this f of z, which is equal to z to the power 1 by 2 on the domain, the slitted complex plane. It is nothing but the set of all complex numbers such that the real part of the complex numbers is strictly greater than 0. So instead of z here, you can replace it with u or write it with respect to z itself. Note that this will be happening inside the UV plane. So you can write in whatever way you are comfortable with. So that is some part of the analysis of the nature of f of z is equal to set square, and we will come to know about more of the same in the next coming lecture. So thank you so much.